An operational amplifier is a DC-coupled high-gain electronic voltage amplifier with a differential input and, usually, a single-ended output. In this configuration, an op-amp produces an output potential that is typically hundreds to thousands of times larger than the potential difference between its input terminals. Operational amplifiers had their origins in analog computers, where they were used to do mathematical operations in many linear, nonlinear and frequency-dependent circuits. The popularity of the op-amp as a building block in analog circuits is due to its versatility. Due to negative feedback, the characteristics of an op-amp circuit, its gain, input and output impedance, bandwidth etc., are determined by external components and have little dependence on temperature coefficients or manufacturing variations in the op-amp itself. Op-amps are among the most widely used electronic devices today, being used in a vast array of consumer, industrial, and scientific devices. Many standard IC op-amps cost only a few cents in moderate production volume. However, some integrated or hybrid operational amplifiers with special performance specifications may cost over $100 US in small quantities. Op-amps may be packaged as components, or used as elements of more complex integrated circuits. The op-amp is one type of differential amplifier. Other types of differential amplifier include the fully differential amplifier, the instrumentation amplifier, the isolation amplifier, and negative feedback amplifier. Operation. The amplifier's differential inputs consist of a non-inverting input with voltage V+ and an inverting input with voltage V-. Ideally, the op-amp amplifies only the difference in voltage between the two, which is called the differential input voltage. The output voltage of the op-amp vote is given by the equation, where AOL is the open-loop gain of the amplifier. Open-loop amplifier. The magnitude of AOL is typically very large, 100,000 or more for integrated circuit op-amps, and therefore even a quite small difference between V+ and V- drives the amplifier output nearly to the supply voltage. Situations in which the output voltage is equal to or greater than the supply voltage are referred to as saturation of the amplifier. The magnitude of AOL is not well controlled by the manufacturing process, and so it is impractical to use an open-loop amplifier as a standalone differential amplifier. Without negative feedback, and perhaps with positive feedback for regeneration, an op-amp acts as a comparator. If the inverting input is held at ground directly or by a resistor RG, and the input voltage VAN applied to the non-inverting input is positive, the output will be maximum positive. If VAN is negative, the output will be maximum negative. Since there is no feedback from the output to either input, this is an open-loop circuit acting as a comparator. Closed loop. If predictable operation is desired, negative feedback is used, by applying a portion of the output voltage to the inverting input. The closed-loop feedback greatly reduces the gain of the circuit. When negative feedback is used, the circuit's overall gain and response becomes determined mostly by the feedback network, rather than by the op-amp characteristics. If the feedback network is made of components with values small relative to the op-amp's input impedance, the value of the op-amp's open-loop response AOL does not seriously affect the circuit's performance. The response of the op-amp circuit with its input, output, and feedback circuits to an input is characterized mathematically by a transfer function. Designing an op-amp circuit to have a desired transfer function is in the realm of electrical engineering. The transfer functions are important in most applications of op-amps, such as in analog computers. High input impedance at the input terminals and low output impedance at the output terminal are particularly useful features of an op-amp. In the non-inverting amplifier on the right, the presence of negative feedback via the voltage divider RG determines the closed-loop gain ACL equals vote VAN. Equilibrium will be established when vote is just sufficient to reach around and pull the inverting input to the same voltage as VAN. The voltage gain of the entire circuit is thus 1 plus RF, RG. As a simple example, if VAN equals 1V and RF equals RG, volt will be 2V, exactly the amount required to keep V minus at 1V. Because of the feedback provided by the RF-RG network, this is a closed-loop circuit. Another way to analyze this circuit proceeds by making the following assumptions. When an op-amp operates in linear mode, the difference in voltage between the non-inverting pin and the inverting pin is negligibly small. The input impedance between AND pins is much larger than other resistances in the circuit. The input signal VAN appears at both AND pins, resulting in a current I through RG equal to VAN, RG. Since Kirchhoff's current law states that the same current must leave a node as enter it, and since the impedance into the pin is near infinity, we can assume practically all of the same current I flows through RF, creating an output voltage by combining terms. We determine the closed-loop gain ACL.